Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. It's a great honor to speak today. I thank the organizers, Professor Ashwini, Professor Sanjay, Professor Lordiraj, for giving me this opportunity. So the title is Mapping Non-Covalent Interactions. Yeah, so I would like to dedicate this talk to Professor Satyamurthy on his 75th birthday celebrations over here. I also wish him continued good health, happiness, and also your inspiring presence in the world of science. I start with this paper by Professor Satyamurthy, co-authored by Professor Subramaniam, my chair here, and written by Parthasarathi. I think he was working with Professor Satyamurthy at the time. The title is Hydrogen Bonding Without Borders and Atoms in Molecule Perspective. Professor Shastri also mentioned this paper, right? See, they have done the atoms in molecule analysis already. You know what is Bayer's atoms in molecule analysis. They have computed this electron density at the bond critical points of several interacting hydrogen bonded molecular structures, and then come up with this beautiful thing, hydrogen bonding without borders. You know, so this paper inspired me, and also encountered in many times in our studies. Yes, Professor Satyamurthy's work inspired generations of theoretical chemists in India and abroad. I am one among them. So he classified these the entire spectra of hydrogen bonds from so weak van der Waals regions around just below 1 kilocalorie per mole to the covalent limit. So this is the beautiful illustration of the hydrogen bonding spectra. So then they classified. It is very difficult to describe how they selected these numbers, like to make it as a moderate hydrogen bond. But it is a rough estimate, like moderate hydrogen bond maybe around 5 kilocalorie range, and then there is a strong hydrogen bond, very strong hydrogen bond, and there is a covalent limit. Now, if you look at the density, see density topography, if you look at it is very rich in features at the bonded regions. Even at the weakly bonded region, you get a bond critical point. But beyond that, if you go away from the bonded region, molecular framework, electron density as such is not having much features. The topography is not so much rich in features, because it monotonically decreases as we go away from the nucleus. But if you plot the Laplacian, of course, you will get a rich topography. Now, so this is actually the nitrocubane. Cubane is connected with the nitro group, and the electron density surface is at 0.005 atomic unit. Now, this is the electrostatic potential definition. If you have the electrostatic potential, already the theoretical part is described in Professor Gadre's talk. Since you have the electronic contribution and the nuclear contribution, so it will show very rich topographical features if you plot outside away from the molecular framework. In the case of nitrobenzene, you see the electron-rich blue regions for the nitro group oxygens, and then you can see that electron deficiency on the cubane. And you can we have submitted a paper on nitrocubanes, the explosive properties of these molecules in collaboration with VSSC scientists. If you put more and more nitro groups, the potential magnitude changes, and which is actually connected with the explosive nature of that molecule. In this talk, I also apply this quantity, electrostatic potential at the nucleus. Every nucleus also you can calculate. Of course, you have to ignore the infinite term. Only the finite part you should consider. That is, so 1 over Ra minus R term goes to infinity. That has to be excluded to get this nuclear potential at the MESP at the nuclear position. Yeah, this part already discussed, so I am not going through that. So del V of R is equal to 0 at the critical point. So Professor Gadre already mentioned that all partial derivatives should be 0 at the critical point. The negative of del V of R is the electric field. It gives force experienced by unit positive charge placed at that R. And then you also have to characterize the critical point using the Hessian matrix and the Laplacian of the matrix, so the Laplacian del square V of R, lambda 1 plus lambda 2 plus lambda 3, basically the sum of these diagonals. All positive is a local minimum, 3 plus 3 critical point, all negative local maximum, and mixed signs will give you the saddle points. And here, for an illustration, you see, look at the formaldehyde. So formaldehyde, the entire topography is shown over here. There is a bond critical points for this structure, and there is also bond critical points. If you look at actually electron density topography, you will get only these 3 critical points. But you can also go derive critical point like 3 plus 3 minimum for the oxygen lone pair, 2 lone pairs, which these 2 minima are connected by the 3 plus 1 saddle. We can also visualize by plotting the electrostatic potential. So minus 38, you will get this region. And also, if you plot a value very close to the 3 plus 1 value, you can see that saddle points surrounded by the electrostatic electron-rich lone pair regions. If you plot a very positive value, you can also see the saddle point over here, the bond critical points, which is another bond critical point for the CO bond, which is the highest positive value. So another illustration is over here, mesh topology of benzoic acid. It's very beautiful. You can see the 3 different electron-rich regions of benzoic acid. One for the aromatic ring, and another for the hydroxy group, the lone pair regions. Another for the carbonyl group. That is having the maximum electron density over there, and which are also surrounded by like 3 plus 1 CPs, 3 minus 1 bond critical points everywhere, and so on. So if you look at acetic acid dimer, so the OHO, the hydrogen bond is there. So there is a 3 minus 1 bond critical point for this, even for the weak hydrogen bonds. Every such, even whether it is strong or weak, you will also derive a bond critical point for that. 3 minus 1 is a bond critical point. And then you can also visualize by, along with the critical point, you can also add an isosurface. Then that kind of visualization is very common in our whatever we published. And this is the kind of a plot Politzer and Murray and so on. They apply this kind of a figure. Like on an electron density surface, plot the electrostatic potential, and on the surface, what are the minima and maxima, plus value and minus value they derive, and they also come up with this kind of a theory like a sigma hole interaction to describe some of the non-covalent interactions. See, this is the another illustration for benzene, aniline, and nitrobenzene. The aniline is electron rich on the aromatic ring compared to benzene, whereas in the case of nitrobenzene, you can see that it is electron deficient. This is the isosurface plot for that. Definitely minus 15.0 kilocalorie MESP is not over there on nitrobenzene. So how much this potential is changed compared to benzene? Aniline is becoming more negative, this is less negative. So that difference itself is an indication, a measure of the substituent effect. That is what we have published in that Jack's paper. Already Professor Gedre showed that. And recently, one of my students, surveyed the whole list of substituents, around 400 of them. And then we found that, this can be correlated with the sigma p Hammett constant. And there are many outliers, so which means that, some of these Hammett constants, we need to revise some of them. And another illustration, another point that we discussed in this paper is, most of the substituents in the organic chemistry are electron withdrawing in nature, you see, and the electron donating substituents are not so many. In fact, if you look at the neutral substituents, the most donating is NN dialkyl amino group. Beyond that, I think you don't have anything that is more electron donating than that. So I think we can improve the chemistry, organic chemistry, by designing more and more electron rich electron donating substituents. So if you optimize any molecular structure, for instance, my advice to you is that you also plot the electrostatic potential. It will give you some more ideas to think about. Like these are actually molecular structures. with the electrostatic potential mapped, the isosurfaces and critical point, especially the minima values. For even cage structures like created by water molecular clusters over here, the cage structure are adamantine and ring structures. Everywhere you can characterize the molecules with the MESP details. Also, the interactive behavior of, for instance, ammonia, this lone pair, how it interacts with the electron deficient hexafluorobenzene. You can definitely study this, the interactive behavior from this MESP, since this MESP lone pair value, if you see minus 73 to minus 46, there is a reduction in the magnitude, which indicates that there is a donation from the ammonia to the hexafluorobenzene. This donation is also reflected over here, minus 11.0 compared to minus 6.6. So there is a kind of a donor-acceptor interaction is over there. It is rather weak over here, but this is proportional to the interaction energy. Yeah, so recently in 2022, around December, we published this review in Wiley Interdisciplinary Research in Computational Molecular Sciences. Around 72 papers we have summarized in this. And I think if you want to know more about how to use this kind of property to study some of these reactions or reaction mechanisms, interactive behavior or aromaticity like that, you can go through this review. So this is already mentioned by Professor Gadre, like Clark's aromatic structures on coronin like things. You can see that the lobes that is electron rich are sextet rings. So I will focus entirely on the non-covalently interacting molecular systems in this talk. These are some of the neutral hydrogen bonded system. This is studied at very high accuracy level, MP4 level, augmented CC-PVD level. We have computed the MESP, and optimization is at MP2 level. So neutral hydrogen bonded systems, anionic hydrogen bonded systems, cationic HP plus systems, and DHP systems. I think Professor Chattaraj asked about some of large variety of like soft interactions and so on. I think our selection includes almost all of them, and there is also lithium bonded systems, H2LiH and H3LiC, and halogen bonded systems where the ammonia is interacting with the halogen bond, so or a sigma hole interactions you could say, and then chalcogen bonded, nicogen bonded, tetral bonded dimer systems. So what we have looked at is, compared to the monomer, you look at the monomer electrostatic features at the first, and then how much this MESP is changed when the dimer is formed in the dimer atoms. For instance, the atoms directly interacting, the nuclei, the potential will be changing. So there is a kind of a donor-acceptor interaction. So the donor atom will lose electrons, and the acceptor, the atom in the acceptor molecule will gain some electron density. So there is a corresponding change in the nuclear potential as well as in the minimum values. If you look at that also, corresponding change will be observed. For instance, in the case of methanol interacting with water, methanol is the oxygen lone pair is the donor, minus 52 in the MESP in kilocalorie per mole, and water minus 50 is the lone pair. So in the complex, it becomes less negative, minus 38, it becomes minus 64. Similarly, all kinds of structures I have shown, all kinds of dimers I have shown, this feature is very much there. That is, there is a change in the potential on the donor and the corresponding increase in the negative potential on the acceptor. So this change can be quantified, and this is for the dihydrogen bonded complex. Dihydrogen bonded complex means in this complex the electron rich hydrogen is interacting with the electron deficient hydrogen. So that is a dihydrogen bonded complex. So there is a change in the potential, and similarly there is an example for halogen bonded complex. So minus 40 was the lone pair on the CN nitrogen, and this was bromine lone pair region. Minus 17 is changed to minus 26, minus 31.4 in the halogen bonded complex. So this change in there is a change in the donor atom, delta V change, and there is also change in the acceptor atom. So the delta change for the donor acceptor, we correlate. There is a very strong correlation between these two. So you can say that there is a hydrogen bonding without borders. So our study also agreed to the first paper that Professor Satyamurthy has, derived from the electron density studies. Yeah, so recently one of my students studied a large set of halogen bonded complexes to verify this kind of feature. For instance, in the ammonia CCl4 complex, you look at, it is pretty obvious that this donates, so it becomes less negative, and this becomes more negative. So in this kind of isosurface plot also you can see. Here what I have shown is the changes in the nuclear potential and the pyridine interacting with another molecular system BROCH2F. See, this region is electron deficient, and whereas this region, the acceptor site becomes electron rich. Then the blue is electron rich region, red is electron deficient region. And in all such complexes also, so why different colors means different type of bases are used, 5 different type of bases on different acceptors. So everywhere there is a strong correlation. So the donor acceptor, how much is the donor acceptor interaction, that width you can actually measure from the delta V value, which is proportional to the interaction energy. And yeah, so we also derived, we also found another interesting thing. See, in this dimer, this pyridine interacting with cyanogen chloride, ClC, and cyanogen chloride, this is the lone pair on the cyanide nitrogen center, and this is on the pyridine nitrogen, and it interacts with the chlorine. So there is a halogen bond. So there is a corresponding change, negative potential is increased on the cyanogen nitrogen center, and there is a dimer formation here. So now to this dimer, cyanogen bromide is interacting. Let us say cyanogen bromide is this one. So this nitrogen is now, this lone pair now is donating to the bromine center. So there is a, compared to this nitrogen is more donating in the dimer. That is what we are saying. So in the dimer, this nitrogen is more donating towards this bromine. So this interaction should be stronger compared to this interaction. That's what, compared to, so I have to mention this one also. Now look at this trimer formation in this way, that is cyanogen chloride and cyanogen bromide forms a dimer here. So in this case, there is a halogen bond over here. This is 3.03, but this is 3 angstrom. So this is stronger because this is more electron donating to this bromine compared to this nitrogen donating to this bromine. And if you look at, yeah, so you can also now think like, this dimer interacting with the pyridine, and then this trimer is formed. Because of this interaction, this bromine, this cyanogen chloride is electron deficient. So this cooperativity is improving, positive cooperativity you can see compared to this bond, compared to which one? This bond is stronger. So there is a positive cooperativity, or you can say that there is a molecular electrostatic potential reorganization theory you can describe here, because whenever there is a donor acceptor complex is formed, the acceptor in the dimer is more donating, and the donor in the dimer is more accepting in nature. So that is what, so this leads to trimers, and this the same theory can be extended to tetramer formation and so on. Or the molecular association behavior you can actually in fact describe based on this kind of analysis. So there is also a strong correlation even for the dimer and trimer, the interaction energy versus delta V values. So this is another example where this dimer formation or this trimer formation can be described in this manner or this manner, and you can see that these two bonds compared to the individual bonds is stronger because of this positive cooperativity. And so in fact there is a strong correlation you can see for the binary, complex, ternary and quaternary systems as well. I also will give you another example where we applied this kind of thing to understand the capacity of guanidine for CO2 complex formation. Guanidine based synthesis is already there, reported in the literature. It is still there for CO2 capture, creating CO2 capture systems. So guanidine, there is a, it's like a immuno form of urea. So there is a imine a group over here. There is a lone pair which can interact with the carbon dioxide. There is a weak non-covalent interaction, 2.7 angstrom. Minus 5.7 is the interaction energy. And if you add more and more CO2 complexes, you can create complexes like this, up to guanine CO2 10 times over here. Total interaction energy minus 43, or interaction energy per carbon dioxide is minus 4.4. Of course, delta G is very much positive over here. So then if you look at the guanidine dimer like this, guanidine dimer interaction energy is minus 12.2. There is a strong hydrogen bond. 2 hydrogen bonds are over there. To this dimer, if a CO2 interacts, there is also a non-covalently interacting, 2.7 angstrom, this CO2. But there is also another interesting one. There is a covalent bond formation between this. If it interacts like this, 1.541 angstrom for this distance. And but this is more stable, minus 13.4, minus 10.1. But another interesting thing is this kind of structure interacts 2 times like this. There is a lot of cooperativity. Now, multiple hydrogen bonds you can consider. So this one is a carboxylate unit is over there. There is another carboxylate unit because of the strong bond. Then there is a lot of hydrogen bonding, which leads to a strong minus 32.8 kilocalorie per mole. So this kind of a structure you can repeat for the trimer, tetramer like that. Compared to any other random structure, these are more stable. And so we have developed this kind of cluster structures like guanidine clusters, and I think it is around saturated around CO2 8 times, around 8 carbon dioxide maximum interaction energy was observed. So this is the result of what happens to MESP if I plot. If you develop like this cooperative hydrogen bonding, the MESP value magnitude minus 68.4, it decreases. I mean, it is, this indicates that it is more and more delocalized because of this multiple hydrogen bonded carboxylate units is formed, which is again hydrogen bonded with the guanidine NH bonds, and then it is totally delocalized. And the electrostatic potential minimum, so from the most negative to the least negative, the maximum interaction energy is formed. So this indicates that it is the delocalization because of this cooperative hydrogen bonding which stabilizes the structure. And if you look at this, this is the value it is starting from this one minus 5.7. You can go up to minus 27.5 per CO2 interaction on this. And yeah, another example is 1H-imidazole 2 amine CO2 complex. 1H2 imidazole. Here it is very, very interesting. This is 1H2 imidazole. It directly interacts with the CO2. There is a 2.75. But if I put one ammonia over here for a hydrogen bonding interaction, that is, this ammonia donates electrons to this to make this lone pair more negative. So when it interacts with this ammonia, minus 67 become minus 72. At minus 72, when CO2 interacts, there is a covalent bond formation. The bond is like, this is like a carboxylate unit. And or in this, 2 are isomers, like bond stretch isomers, and with almost a similar energy. I will conclude this in 2-3 minutes. Yeah. So then we also looked at this 8 octamer of this amine and octamer of CO2 cluster. If it interacts, a random complex formation is something like this, so minus 170. But this well-organized, cooperatively binding hydrogen bonded structures with more of delocalization of the electron density, it becomes minus 290 kilocalorie per mole. And because of that bond stretch isomers, this one against this one, we also can get a transition state for that. And with this, we can also describe a non-covalent to covalent bond territory also. This is the transition state is the boundary line. So which means that this is through this a non-covalent complex formation and then cluster formation leading to maximum stable complex like that. Yeah, so in this talk, what I have convinced you is, MESP is indeed a powerful tool to interpret and predict not only non-covalent interaction, chemical reactivity as such. So that's it. I thank my teacher, Professor Gadre, for mentoring throughout me and also giving me encouragement, and also very, very fruitful collaboration. We wrote some fantastic papers together. And also I thank all my students, around 18 students completed PhD, and also thanking the funding agencies. Yeah, thank you very much for listening.
Swayam Prabha. Digital India. Educated India.